All right. I think we have enough seats for all the speakers. So this is going to be a session on glTF. We have lots of awesome speakers here. We'll shuffle, but we'll have a Q&A session at the end. And so store up your questions. The trickier, the better. And we can ask questions to any of the panelists here today. So let me introduce myself. I'm Neil Trevett. My day job's NVIDIA. I'm president of the Khronos group, so I'm emceeing today's session. The SUGAF organizers have asked us to confirm to everybody that photography is welcome. You can take any photos you want, but we will also be uploading the recording and the slides to the Khronos website. That's the URL on the QR code. And it should be up there within a few days. So we're here to talk about glTF today. So I suspect everyone here knows glTF is an open and royalty-free file format designed for efficient transmission and loading of 3D models. We like to say it's the JPEG of 3D. We're aiming for 3D to be pervasive. You can load it and run it on any device in the known universe. And it's a JSON-based standard, but it does have a binary encoding. So you might see glTF files, you might see GLB files, which are the binary encoded files that packs everything into a single file. One of the nice things about glTF that we'll be talking about, it has a very well-defined physically based rendering model, a PBR model, which means you get good visual effects across all these different devices. And glTF is highly extensible, and we'll be talking about how we're using that to build out the glTF ecosystem during the session here. So, because glTF has a very focused mission on being kind of the last mile delivery and transmission format, very efficient to use, it's resulted in glTF being achieving its mission and being available pervasively across many different platforms, applications, engines, you name it, glTF is running on it. On the left, we have tools. On the right, we have engines, web engines, applications, platforms, that are using glTF. It's pretty much everywhere. Some of the most recent announcement, Android XR, which is going to be, I think, very significant for XR devices, is pretty much based on glTF and for its 3D asset model. And people might have spotted the news on Monday that Microsoft announced that now Copilot can turn your 2D photographs into 3D models, and it exports those as GLB files. So one more logo to add to this slide. It's a full-time job keeping this slide up to date. So glTF, this is a slide I like because it puts glTF in the center of the universe. But of course, there are other file formats out there. Another awesome file format is OpenUSD, which is coming from the movie and complex and very sophisticated authoring perspective. So the two standards are coming from different perspectives. There's going to be overlap, but in general, they are very complementary, and glTF loves working with OpenUSD and working to make sure that our roadmaps are aligned and we can enable people to transfer their assets from one to the other, as OpenUSD becomes defined and comes online. But from the glTF point of view, we're transmission. That's our basic and primary mission, getting assets into devices. To do that, we have a bunch of tools. Leonard's going to be talking about some of the community tools that we are building to make that a reality. Of course, people do want to convert in and out of the authoring formats. And people, although glTF is not intended to be an authoring interchange format, that's more in the OpenUSD domain, people do want to import glTF into their tools for remixing and then re-exporting. It's like PSD files. If you're doing Adobe Photoshop, that's your kind of your master file. But people all the time bring JPEG files into Photoshop too, because that's what they have available, and they want to remix and process them too. One of the nice things about glTF, and we worked hard to make this happen, is that glTF is an ISO standard. So ISO is the International Standards Organization. We go through the ISO process. It really is quite a rigorous process to make sure that the specification is well written, it's pervasive, it's well adopted throughout the industry. So it's a big endorsement to the standard. The glTF 2.0 is an ISO spec. It became an ISO spec in 2022. And that means that a lot of people, even more people, are interested to use the glTF specification as a standard. And we're very happy to be working with a number of vertical domains who are adding value to the foundational glTF spec. Domain experts who are really adding their specific knowledge on how they want to use glTF, and we have a number of them here today. So 3D Tiles is a community standard from Open Geospatial Consortium. Using 3D Tiles is a set of glTF extensions for geospatial. Sean's going to be talking about that. We're working with the VRM Consortium, which is a consortium based in Japan, creating really the most widely used avatar format. Its target market is vlogging, but there are millions of avatars that are being created and used over in Japan, and it's becoming a global standard. That's another set of glTF extensions, and we're working with the VRM Consortium to have an avatar roadmap. MPEG is using glTF to bring 3D into their video streaming portfolio. X3D now has glTF as a payload, and even PDF now has support for glTF in their ISO standard, which is the PDF standard. And I think we'll see more and more of these verticals appearing over time. And we're going to be talking about some of these in the session today. In fact, I'm going to just give a sneak peek on what Sean's going to be talking about. The 3D Tiles from OGC, just kind of give an example of how this kind of relationship between Khronos and other standards organizations can work. 3D Tiles has done a great job in bringing advanced functionality, particularly for streaming extremely large data sets, 3D data sets, in an interactive way. And so they've really been the bow wave of creating streaming and spatial handling of large data sets. But that kind of capability is now becoming of interest to the broader community. There are lots of people that want to stream gigabyte or even terabyte sized glTF data sets. So we're beginning to work with the OGC and with Cesium, the originators of the 3D Tiles standard, to bring the functionality that is becoming widely demanded by the industry into the core glTF specification. So we're adopting some of the functionality that's been pioneered by the geospatial community and well proven in the geospatial community. But it's a bi-directional value, because whilst we're doing that, 3D Tiles is benefiting from using the expanding base of functionality that is in core glTF. So we see this as a upward flywheel effect, and Sean is going to be talking in more detail about how that can work out in practice. But it's an interesting example of how working with domain-specific standards organizations can really benefit both parties. Another good example is the VRM cooperation. So VRM 1.0, which is the avatar format, is a set of glTF extensions. We and the VRM consortium want to build out a foundational model for how we can bring avatars using glTF in a whole range of other domain targets, not just vlogging. I mean, there's Avatars can be anything from a cartoon all the way up to photorealistic, fully human representations. So there are lots of different markets and use cases. So one avatar standard is never going to meet everyone's use cases. So the idea is to build a foundational set of glTF extensions that can be built into the glTF standard itself, and with enough flexibility that people can then build their own domain-specific extensions on top, just doing the bit that they need to adapt the foundation into their specific vertical, not having to reinvent the whole stack every time. And the VRM Consortium, now shout out to the VRM Consortium, they've been very cooperative, and we're figuring out how we can help them do that and how we can leverage the momentum that they have whilst they transition to using this foundational network whilst maintaining backwards compatibility in their ecosystem. So it's a very interesting and productive discussion that's ongoing, and another good example of cooperation with the vertical. Inside the working group, as I mentioned, PBR is really one of the strengths of glTF. The PBR group inside glTF doesn't try to invent new technology, but it takes well-proven technology that's been widely used in the industry and then very carefully and specifically defines it for use within glTF, and we take a lot of care to specify every nook and cranny of how PBR is defined. That's what gives glTF its portability across many different devices. There's no ambiguity on what a glTF PBR material means. Everyone can process it the same way. Everything is very carefully defined. We're also working in the material space with other standards organizations. ASWF, the Academy Software Foundation, has OpenPBR, which is coming out of Adobe and Autodesk, and Material X, both getting good adoption, and we want to be in alignment with that too. So we are working closely with the ASWF. Inside the working group, the next our PBR functionality comes in waves. I think we're up to wave 5, if I've counted correctly. Yes, wave 5. Yes, wave 5. Which is diffuse transmission and volumetric scattering. So diffuse transmission is when you hit a volume boundary, you can modulate the light. Volumetric scattering is where you have a volume with tangible thickness. The light will be diffused, so you can get another wave of physical effects for your lighting models. And the Material X and glTF interoperability, we can now represent the glTF PBR model as a Material X graph. And we're looking to have even closer cooperation between the glTF PBR model and Material X as we go forward. Something that's not shipping yet and is just a discussion right now, so I don't want to misset expectations. This is going to ship tomorrow, but I think this is an early indicator of a really significant development, and that of course is AI in graphics. I think it's going to affect almost everything. And in the domain of glTF, I think AI is going to enable us to do some things that are pretty magical. Neural graphics is based on multi-layer perceptrons, which is a very small neural network trained for one specific task. So it's not like ChatGPT, which is a large language model. This is a small, fully connected network. You train it, and then you execute it, inference it in your shaders in real time. And so one use of that is neural textures, where you train a neural network specifically on a multi-channel texture. And when you execute that MLP in your shader, And the Vulkan API is putting lots of intrinsics into its APIs, so you can do that very efficiently. You can actually generate output pixels. And I've seen one of the most freaky demos I've seen over the last year or so is, people here might know the flight helmet, which is 180 megabytes of texture, and it runs interactively. The demo I saw was, we've trained a neural network on all of the whole texture atlas for that model, 180 megabytes multi-channel texture, trained it into a set of about 2 megabytes of weights running on an MLP in Vulkan, and it just looks exactly the same, except there's no texture. So you don't have to carry around 180 megabytes of textures, you just have to carry around 2 megabytes of weights for your neural network. A radical decrease in size. Once the hardware is pervasive to run the neural networks at full speed, and the first wave of that is already here. Now, this is going to enable us to really have a radical reduction in asset sizes for many types of application. So watch out over the next year or two. The first proposals for what we need, the machinery that we need for neural texture, neural graphics are already being made into the working group. So I think this will happen over the next year or two. And I know this is a very detailed slide. We're not going to go through it in detail, but you can look at it when you download, or you can take a picture of it. But this is what the working group is working on. The left-hand column is what's shipping today. The middle column is what we hope to, we're working on right now, and we're hoping to ship in 2025, 26. So that includes Gaussian splats that we're going to be talking about in the session here, billboards and voxels on the geometry side, looking a little bit further out on the geometry track, 4D splats rather than 3D splats maybe. A lot of people are asking for quads in glTF. They've been asking for many years, and I think we're getting close to maybe doing it. Maybe subdivision services, that's a discussion as well. The concern has been, would it run, would the necessary processing run okay on a mobile phone? And I think everyone is now comfortable that it would. So maybe that would be a great thing, because that's another way of decreasing asset size by having more compact and processed geometry. We have external references. This is something that we've been discussing for a long time. We have the idea that we may do GLX as an initial file format, which is basically a list of external references. You can compose scenes. You can use it for all kinds of asset management, LOD management and streaming. Lots of discussion going on with the 3D tiles folks, and Sean is going to be talking about that with the quad tree and octree spatial subdivision, and how, again, that loop we were showing earlier, how can we make that work in practice. On the texture track, we talked about Material X, node graph. We are looking at procedural textures right now, looking a little bit further out where it gets more tentative. HDR textures, the neural textures that I was just briefly talking about, video textures are being asked for as well. Materials. Is Ed here? I think Ed's here. I saw Ed earlier. So specular edge color, diffuse roughness. So wave 6 of our PBR roadmap, and more compatibility with OpenPBR and Material X, potentially importing at least partial Material X graphs. Animations, a big topic, and we were talking about VRM. A big topic is avatars. I think that probably will be the use case that will drive the need for more advanced animations. Skeletons, rigging, and multi-track animations. That's a very active track of discussion right now. Lighting. We have the scenes with GLX, so you can have multiple assets composed into a scene using GLX, and that includes multiple lights. So if you're bringing multiple lights and composing them into a scene, how do they light each other's assets? So that's something that we're working on right now. Interactivity, we're going to be talking about that today. That's a big piece of functionality that we already have working and will be shipping imminently. That is going to be kind of a long-term evolution as we figure out more interactivity to build into glTF once we have experience with the first generation. Physics, Eoin's going to be talking about that. It's rigid bodies today, maybe at some point, maybe deformable bodies. So Eoin has convinced me that it's super complicated, but Eoin can talk more about that. And media, we are building audio. That's an active project right now. Maybe in the future, physically based audio, video synchronization, maybe even volumetric media. The first requests for volumetric media are beginning to come into the working group. So hopefully that kind of gives you a flavor for the kinds of things we're talking about. If anything is of interest to you on there, and you would like a voice and a vote and an inside track on how it's developing, please get your company to join Khronos. Everyone is welcome, and any member of Khronos can come and join in the working group discussions. So this is a condensation down into the next few quarters. This is what we're really working on right now: interactivity, Gaussian splats, physics, PBR, Wave 5, avatars, and complex scenes. So the rest of the session, we're going to be going through some of these topics to give you the next level of detail. Thank you to all of the speakers that have put a lot of effort into creating all the materials that we're going to be discussing today. We have Eoin from Microsoft going to be talking about physics. We have Eva from Meta who's going to be talking about interactivity. Sean from Cesium/Bentley going to be talking about complex scenes. We're very honored to have Michael here, along with Adam from Bentley, to talk about Gaussian splats. Leonard from Khronos is going to be talking. Leonard runs the tooling subgroup inside 3D formats, going to be talking about our tooling. And last but definitely not least, Eric, who's representing the 3D commerce working group inside Khronos, which is the group inside Khronos that actually figures out how 3D commerce wants to use glTF and gives us super valuable use cases and requirements so we can make glTF better. And Eric's going to be talking about our 3D commerce efforts. So that's enough for me. Let's get into it. So Eoin for glTF physics.
All right, thank you. So I'm going to talk about a physics extension for glTF. And the first thing I need to address is what is physics, because literally everything is physics. So it's a big topic. Today, we're just focused, as Neil says, just on rigid bodies. So that's objects that don't change shape. The reason we do this is there's lots of simulators for this kind of physics simulation out there. And the verbiage they use and the concepts they use are very similar. So there's a lot of consistency between those packages. They're all very mature. So it's really ripe for putting some standards on this and saying, here's how you express these concepts in a file format. By contrast, deformable objects, there's a lot more different types of simulation, a lot more variability. It's a lot harder to design a standardized way of saying, this is how you describe those things. So we're going to do the easy stuff first, and we'll tackle the hard stuff when we get to it. So what can you do with physics? Why might you want to put rigid bodies into an asset? If you're doing video games, you're almost certainly using rigid bodies for your game assets so that players can interact, move things around. And it adds a level of interactivity, different kind of interactivity than Eva is going to talk about, but lets you play with the assets, and you get a believable procedural animation out of it, and allows users to play with an asset in ways that they can't with static mesh. And one of the things physics is really interested in is efficient collision detection, which enables scene understanding in new ways. So you might position this gramophone, you might want to go ask a query of the scene, how can I efficiently place this on a table? Where do I need to put this so it's actually resting on the table? And physics enables you to do those kinds of queries very efficiently. So I'm going to go high level through a couple of the concepts that are in physics, not everything, but just the stuff we need to get started and do some fun simulations. So the first thing we need to do is address that efficient collision detection. So we have shapes, and we've described an implicit shapes extension, which describes a couple of basic shape types. They don't do anything, they're just document level data definitions, and let you get efficient sphere-sphere collision detection where you don't want to do that kind of stuff with a triangulated mesh. So there's a bunch of stuff in there. But physics itself also wants some less simple shapes, so we want to be able to describe collision shapes with triangle meshes and convex holes. And the combination of these might allow you to represent an asset in two different ways. So you might have on the left your render geometry, which might have thousands of triangles, and on the right you've got a set of convex holes. That's your physics representation, and that's what the physics engine sees. And it's an approximation of the render geometry, but it's much more efficient to simulate. And that's the kind of things we use to describe how things should collide. Next thing we want to do is say the simulation should be able to move an object. So we have the concept of a motion, and it's something you attach on a node and says, simulation, you take control of this. And it describes how the object responds to forces. It has velocity, mass, inertia, and lets the simulation know how to handle an object and what to do with it. And that's all we need to do a basic simulation. So we can take those two things and we can put them onto these shapes and we get a simulation. And that's great. But it's a homogeneous set of assets. So next thing we want to do is add some more believable behaviors to those things. So we need a physics material. So we want to say these basketballs and bowling balls should bounce differently. So we have friction, restitution, and a simple mixing model that allows us to do a simulation and get much more believable behavior. And now we're starting to see, this kind of rich, interesting simulations coming out of the physics. The last thing we want to do is joints. So a joint connects an object together in some way. Think of it like a hinge on a door, or an elbow on a character, or the chain on this wrecking ball. There's a lot of flexibility in these joints in what they can describe, but allowing you to connect two objects together now makes really, really interesting simulations. So let's put this all together. You might recognize this asset. This is one of the glTF sample assets, the stained glass lamp made by Eric. And it's a static mesh, but if I go along and I rig it up with some physics, we can go in, we can pick all the individual beads and we can move them around, they can hit each other, and you've no longer got a static mesh anymore. It's a much more interesting asset. We can pick up the whole thing and shake it around, and it looks great. It's super fun to play with. But if you took this to your marketing department and said, put this on my website, they would probably kick you out of the room because this isn't a good look for your product when you're trying to demo this in augmented reality. So physics still allows you the control to say, okay, I want to override that behavior. So here we've got the same asset with one setting changed, which is that we can't rotate the base of the lamp at all. No matter what you do, no matter what way you pull it, if you put it precariously on the end of your table, it's not going to tip over. And that'll get your marketing approval, and you can put that on your website and sell some lamps. So where are we with those two specs? So the KHR implicit shapes is a little further along. It's simpler. There's less in it. There's more users of it. So it's at a release candidate state, ready to go. Physics rigid bodies, a bit bigger. It's currently being reviewed. We're open to any feedback that you might want to give us on things that are missing or things that are maybe not described as well as they could be. If you want more info, there's a QR code here. This will take you to a GitHub repo. What we've got here is the documentation for the spec itself, the JSON schemas. There's a bunch of the sample assets. There's 60 test assets. We're going to add more over time, just testing different combinations of all the options. And there are links to importers and exporters. So all the videos I showed were produced with Blender, exported and imported into babylon.js. So if you want to send feedback, you can log issues there, or you can, if you want to email me, there's my email address. I'd be particularly interested in hearing if you want to use the implicit shapes for some other new pieces of functionality unrelated to physics. So that's exciting to me. And that's all I have to say on physics. So with that, I'll hand you over to Eva to talk about interactivity.
Hi everyone, my name is Eva from Meta, and I'm here to talk about interactivity. So what are we trying to do with interactivity? It's a description of how content responds to user interactions or events. It's portable, secure, and visually accessible authoring. We define a node-based graph. It's a sweet spot between flexibility and security. It avoids non-portable, like custom JavaScript that lets you like tap to play or trigger anything that depends on a specific VM. It's a distillation of all the different popular game engines out there. We took inspirations from visual scripting in Unity, blueprints in Unreal, and NVIDIA Omniverse action graphs. There's a lot of different use cases for this. You can build mini-games with interactivity, educational resources, and do design reviews. There's e-commerce applications, and you can do procedural animations. So here's an example of interactivity in e-commerce. This is a configurator where you can, your potential customer can directly customize what the product can look like directly. So they can choose different color of the car, for example. So our approach to interactivity is enabling developers to create portable node graphs stored in the JSON format, similar to the rest of the glTF format, and defines how 3D content respond to user actions and events in a platform-agnostic way. So it will work on mobile, on AR, VR headsets, and whatever platform we support. We want to expand the glTF event integration. So there are a range of events we support, built-in events like onStart and onTick, input events like onSelect, onHover, and then each individual asset can also define custom events. The graph also defines different actions that you can do in response to the user events. Any scene state can be used to calculate or animate the mutable properties in the glTF. So, for example, we have control flow, so your typical for loop, if else, switch, that's all available. You can control animations. You can play and stop predefined animations in the glTF assets. You can also read and write glTF object model pointers. So, for example, you can change the base color factor of a PBR material, the weight of a mesh, the transform of nodes, for example. You can also define custom variables in the graph, similar to a program, and read and write those variables at runtime. You can send and receive custom events. So this allows you to reuse part of the graph and create like function in the glTF interactivity. There are common math operations directly supported, trigonometry, quaternion operations. The common operations are supported. Yeah, so going into a little bit more detail of the nodes that we support, we have math nodes, control flow, state manipulation nodes, I mentioned in the previous slides, so there are like variable nodes, pointer nodes for direct manipulation of the glTF asset properties, animation control nodes to play and pause, control existing glTF animations. There's event nodes like onTick and onStart, as well as custom events. For other extensions can also define their own object model pointers that can be read and write from the interactivity extension. So one example here is KHR node visibility. So you can change a node visibility at runtime through the interactivity graph. So here's an actual minigame, Whack-A-Mole, built entirely through interactivity. As you can see, you can hover and click on the different items, and then it will disappear and respawn randomly on the plane. This is actually a very complicated graph. There's 518 nodes, 19 type of nodes, and 14 variables powering this under the hood. Here are more examples. There are very simple graphs with just a few nodes, and you can play and control animations. And then there's more complex graphs, like I showed before, where you can do a lot more interesting stuff, like building a minigame. We're designing this with security in mind, so we don't want to allow any dynamic allocation at all. You can sort of imitate dynamic instantiation by toggling the visibility attribute. But that's pretty much it. We don't want to have dynamic allocations of any other kind. We don't allow networking access, we don't have file system access, and we don't have multi-user capabilities. The runtime implementations are also expected to enforce or limit the node execution time and restrict memory allocation to guarantee consistent performance. We don't want to run into like an infinite loop on a frame and then degrade the engine's performance. So here are a list of authoring tools and engines that either already support interactivity or have plans to implement it. I will call out the very interesting thing here that it's the Unity glTF exporter. So this allows you to export a Unity scene with visual scripting as a glTF with interactivity. So you can take advantage of all the authoring tools in Unity to create the visual programming, but then export it in a very portable and cross-platform format as a glTF. So where are we taking this in the future? Any other upcoming glTF extensions can extend the glTF object model, and these can be modified at runtime through interactivity. So some of the physics extensions that we just talked about can be exposed to interactivity. And for example, you can change the friction of an object at runtime. Interactivity in complex scenes with multiple external reference assets. This will allow us to have more modular and reusable graphs at the individual scene node level instead of only at the asset level. So the Whack-A-Mole example I showed earlier could be reduced into a much smaller graph where you can have an interactivity graph attached to the individual like modes instead of a giant graph. This will also allow interrupt between different GLF sets in the scene. So you can send a custom event from one glTF to another, and then coordinate the experience together to build something more complex. We also want to add audio and video playback control nodes in the upcoming audio and video extensions. And here are a list of resources for interactivity. We have a web-based authoring tool. There are a lot of sample assets and viewers. And then the Unity glTF plugin I mentioned for exporting directly from Unity. And then finally, please share any feedback for us. We're trying to ratify the spec this year, hopefully. So if you have any feedback, we love to hear it. And then I'll welcome Sean to talk about glTF complex scenes next.
All right. Hey, everyone. So I'm Sean Lilly from Cesium/Bentley, and I'll be talking about glTF complex scenes. So how do we have glTFs that reference other glTFs to create more complex environments? And a lot of this is inspired by our work with 3D tiles. So 3D tiles is an open standard. It's a OGC community standard that Cesium created. It's really designed for streaming the built-in natural environment. So all these different types of data like 3D buildings, point clouds, photogrammetry meshes, vector data, voxels. All this needs level of detail and needs streaming capabilities. So 3D tiles was created to solve this problem. And ultimately, 3D tiles defines the spatial hierarchy. So you have like a root tile, then you have children tiles, and so on. There's concepts of geometric error, so that tells when a tile refines to its children. And then every single tile is really a glTF model. So the root tile is a glTF, the leaf children, or the leaf tiles are glTFs. And the glTF is what contains the actual geometry, textures, and materials of the content of the tile set. And then your glTF can have metadata inside of it as well, and you could do runtime styling. Over the course of both the glTF and 3D tiles history, we've really taken advantage of the glTF ecosystem within 3D tiles. So glTF has, it's a really efficient format, and it has a lot of extensions that are very, very nice for us. So like Draco and MeshOpt for geometry compression, KTX2 for texture compression, GPU instancing, PBR next. And then recently we've been introducing some new extensions. So one you'll hear about from Adam is our Gaussian Splats extension. We also have a voxels extension that's also open in the Khronos GitHub repo. These are both draft, and we're definitely welcoming any feedback for these. And we also are doing a lot with AEC rendering, so how to do efficient polyline rendering, how to do billboards, outlines, edges, all sorts of things related to architecture, engineering, and construction. So this is sort of what we're looking at now is we have such a good collaboration like between the glTF and 3D tiles ecosystem. But what if we brought some of the 3D tiles concepts back into the glTF ecosystem? So things like spatial subdivision, level of detail, and external glTF references. We've especially seen a lot of need lately of the ability to represent complex scenes in glTF. And we think a lot of the concepts that we've already sort of tried and tested in 3D tiles, we could bring into the glTF ecosystem. So that's through the whole glTF external references effort, which we also call GLX. This is sort of a conceptual model of what this looks like. So glTF is the assets, it's the geometry, materials, and textures. And then GLX is sort of this layer above that represents complex scenes. Whether it's a separate file format or a set of extensions is still kind of up in the air at this point. But GLX would contain the spatial subdivision, the level of detail, and the external references. So you can create complex scenes. And then the layer above that would be 3D tiles. So these would be like geospatial specific extensions that would be like, for example, like bounding volume types that may not be relevant for all use cases, but may be important for geospatial. And then coordinate system information or vector data, just other examples that are like geospatial specific. So I do have a demo that I want to show. I've been prototyping what glTF external references might look like. And so I have a few different use cases. So we'll see how this goes. Okay, I'll try to, there's a slight discrepancy between what I see on my screen and what's on the monitor, but I think I'll be able to make it work. So first I think I'll show maybe what some of this looks like at the glTF level. One second. All right, so here we have, I'm also gonna make this a little bit larger.
You can rest it down on the keyboard.
Okay.
Yeah.
All right, so here's a glTF. I'm calling it glTF with discrete LOD. So this is basically a glTF that references 3 other glTFs. And I'm using a couple different non-official extensions yet. These are just sort of placeholders. But the important one is the KHR external references extension. And then scrolling down, if you've seen what GLX looks like, this is very similar. There's a top-level list of assets. So this will be like your external references as GLB files. And then you have your regular scene and you have your nodes. Each node can then point to an asset. So this one's pointing like to the dragon low.glb. So that'll be our low detail content. And then it has like geometric error and bounding volumes to know when to refine and how to do like frustum culling and other things. And then its child will be pointing to asset 1, which will be the dragon medium.glb. And then that one will have another child, which will point to the dragon high.glb. So then I prototyped this in CSIM.js, kind of almost just leveraging like the 3D tiles code that we have. So here's loading that GLX, or really that glTF with external references. And I can zoom out and see the low level of detail, zoom in, see the medium, and then as I zoom in closer, I see the high level of detail. So we essentially have a glTF that's referencing all three of these level of detail. And then for the second example, so I kind of did a bunch of work in Blender yesterday to try to like separate the Sponza model into separate parts. So we have the base Sponza model. So yeah, I can't really full screen or else it'll get cut off. But yeah, Sponza model, and then we have the plant, and I've kind of made that its own asset, plant.glTF. And we have 6 different references of that. So we have our glTF that's like the geometry just for this, like the base Sponza scene, and then we have 6 external references. And then like if I zoom in, I don't have it here, but like because there's all these bounding volumes, and we can then do frustum culling. So actually the 4 plants that are behind me aren't even being drawn at the moment. So Sponza is like a relatively light model, but imagine if this was a lot higher, like triangle count. This would be pretty important to just have good performance, to split up the scene like this. And then I have other ideas for demos. Like, I mean, ultimately we want to like take 3D tiles and be able to replicate it in glTF external references. And that's like gigabytes to terabytes of data. I think the concepts that I've shown here actually still apply even for that scale. So just a sneak peek of sort of some of these demos I've been working on. And I think that's it for me, and I'll hand it back over.
Awesome. Good morning, everyone. I'm really excited to be talking to you about 3D Gaussian splatting in glTF. Definitely this week specifically at SIGGRAPH, we've seen so much excitement surrounding the world of Gaussian splatting, and so I'm excited to kind of talk to you as to some of the reasons why that is. So just as a quick little overview, Gaussian splatting was published in mid-2023, and basically it is a radiance field representation that renders in real time. And what it allows us to do is it allows us to reconstruct traditionally difficult details. This could be things like thin structures, semi-transparent objects, really highly reflective surfaces, and we can also reconstruct it in very lifelike 3D fidelity. And we can see this as well translating across a multitude of devices, whether you're on like a workstation computer, if you're on a mobile device, or any really modern architecture, you're able to actually interact with this type. So we began to take a look at standardization earlier this year. Obviously, this is a very quickly and rapidly evolving field, and it is the first radiance field representation that is being actively adopted and built into industry. And so we're seeing support being added by Esri, DJI, Bentley, and there's actually quite a few more that will be coming over the course of the next few months. So we also take a look at kind of comparing before with, like, say, photogrammetry to now Gaussian splatting from this capture provided from a construction firm called Skender out of Chicago. We can see that we can actually really start to reconstruct some of the more thin details, like the glass on the building, as well as really getting deep depth of field into the background and cityscape as well of it. So now we can take a look at, why would we want to pair Splats with glTF? And Splats really complement meshes and point clouds. They don't replace them. It's something that you can add on additionally to get a really lifelike 3D representation of a space that will render in real time. So there are currently 2 extensions being developed currently. They are KHR Gaussian splatting and KHR Gaussian splatting compression SPZ. There's been a ton of really great work on both of these fronts, and when Gaussian splatting was first published in 2023, we've already cut a considerable amount of the file size, thanks in part to Niantic's SPZ. So what we're really getting here is a large win in the realism department. We're able to really model and reconstruct lifelike 3D, and we're also getting very strong performance for large real-world scenes, which we'll actually take a look at through implementations like Bentley and Esri. On the other side, glTF has been widely adopted and is easy to integrate, making it a really nice natural pair for Gaussian splatting. And it's also portable across engines, viewers, and pipelines, which is something that I think is really needed for Gaussian splatting to continue its meteoric rise. We also can take a more clean separation of both structure and compression and make it a more interoperable path for storage, streaming, and tooling. And so I really think that having glTF support makes Splats accessible to existing 3D ecosystems and continues the trend of more and more industries continuing to adopt the technology. So with that in mind, I'm now going to pass it over to Adam to go into a little bit more detail as to the different extensions that are being proposed.
All right, thank you, Michael. I'm one of the co-authors on the KHR Gaussian splatting extension and the KHR Gaussian splatting compression SPZ. So for the KHR Gaussian splatting extension, we're using this to kind of build a foundational basis for building Gaussian splatting as it evolves. So we want this to be very extensible. We want this to be a really solid foundation for the future of Gaussian splatting, because ultimately we don't want to do R&D by committee, but we do want to actually start to allow people to kind of have some level of kind of foundation that they can actually start using Gaussian splatting in production today and actually be interoperable across multiple engines. So to do that, what we're doing is we're actually using the point primitive, and we're using base glTF spec attributes for the position, the diffuse color, and the opacity, which we're encoding into the color alpha channel. Rather than actually storing the diffuse component as a spherical harmonic, we are actually turning that into a GPU-ready diffuse color component, so we're doing that math. And what that allows us to do is that's going to allow for graceful fallback in those renderers that don't support Gaussian splatting at first. Well, if you load up a glTF there, you'll still see something. You'll see that very sparse point cloud. But it won't actually use the additional attributes that are used to actually render the splat. So those extension, the extension defines those additional attributes as the rotation, the scale, the spherical harmonic coefficients, which are completely optional. So in the event that in the future we actually have PBR lit Gaussian splats, you can just, those spherical harmonics, they're optional, so you don't actually have to use them for your lighting anymore. Or if there's something else that comes in for lighting, you'll be able to do that instead. And then finally, we're defining a set of rendering hints, and we need help with this. I know that the OpenUSD guys, if you saw my presentation yesterday on interoperability with them, we both need a lot of help here about what rendering hints your renderers need to actually render splats consistently in your engine. We're taking those in, we're looking at them deeply. Right now, today, what we have is we've got the shape of the Gaussian, we've got projection used, and we've got the sorting method used. We're trying to make these open fields, so as time goes on and things evolve, we'll be able to actually keep those up, and they're not going to be, I guess the values are not going to be deeply normatively defined, so we'll be able to come in and do non-normative updates of saying, hey, like this is what the industry is using here, so you should probably use these, but that's just a strong suggestion. And this is actually working today, and at Cesium Bentley, we do have this in production, and I'll show you a video of this factory, this gas refinery here in a little bit, but yeah, so that's actually glTF, and that is working in Cesium.js. So we also realized that Gaussian splats today, there's a lot of data, especially when you consider the spherical harmonics. So we do need a compression method, and there's been a lot of debate over what compression method we should go after first. We decided to choose SPZ because it's in production. Niantic Spatial are partners of ours, and we have a good relationship with them. And additionally, SPZ does a really good job and is relatively easy to implement in engines because of the library itself. So we have the KHR Gaussian splatting compression SPZ extension. It stores the SPZ blobs and glTF buffers for efficient delivery. You can take that SPZ blob and just treat it, send it through the SPZ library, get the data you need, and then you're good. So you can either stream that SPZ directly to the renderer if you have a renderer that supports the SPZ, or you can decompress it from the SPZ library into attributes if that's what you prefer. There's a spherical harmonics choice per asset, so if your assets have no spherical harmonics, which is actually pretty common in AECO, you don't need to have any, but then as you go up, you can actually have the first degree, second degree, or the third degree spherical harmonics if you want all of them. It is open source and it's MIT licensed, and what we've seen is that it's about 90% smaller than Ply while preserving visual fidelity. And we're actually working with Niantic Spatial to actually improve SPZ over time. Most recently, we worked with Esri and Niantic to help them fix a small rotational precision issue, and so that has been changed over to using smallest three quaternion components, which gives higher precision and it gives better looking splats with basically the same compression ratios, which is wild. And so we are doing validation on real geospatial sets, and yeah, you know, please try it out, see if it does what you need it to do. And the good thing is that say that SPZ doesn't fit your needs, well, the idea with the baseline splat extension is that you'll be able to extend it and you'll be able to do other compression methods on top of that. So right now, you know, for the AECO and geospatial areas, we're using a lot of SPZ. Well, you know, maybe you want to use MeshUp, maybe you want to use SOGS or something else. Well, we can actually build extensions that can do those compression formats elsewhere. So, and this is honestly to be very future looking, because we want this baseline extension to kind of survive the test of time as long as splats are in glTF, or well, Gaussian splats are in glTF, and we want to just provide that future. So here's that video that I promised of the refinery, and you know, this is a great example of how all those thin structures on a traditional photogrammetry that would be completely just like optimized away effectively. And you know, here you can see that I think this one, because I actually trained this myself on my machine with the source data that a colleague of mine at Bentley gave me, and I think it's only 400 photos, which if you're in the photogrammetry field, 400 photos for something that's of that fidelity is just wild. So yeah. And I'm going to pass it off to, back off to Michael to finish it up.
Cool. Yeah, thank you, Adam, for taking us through that. And oh, thank you. So yeah, as we're kind of like just showcasing, there's a ton of excitement about this technology, and there are a lot of industries that are currently investigating implementing it right now. You know, we kind of just like focus on geospatial and AEC in this talk, but I know firsthand, you know, from even just SIGGRAPH, you know, NVIDIA just announced the new rec library for Omniverse and IsaacSim for both robotics and simulation-based purposes using Gaussian splatting. And you know, we're also seeing tremendous interest in e-commerce, hospitality, as well as also federal applications, and including also sovereign AI as well as insurance. So there's a lot of industries that are really interested in adopting this technology, and if you are also seeing a value in your own industry, please go ahead and scan the QR code and, you know, let us know what you would really want to have in this standard to make it into a more interoperable 3D future. So we're really excited to see the progress of this technology, and we're excited to help make it into a really great standard for you all to use. So with that, I am now going to pass it over to Leonard, who's going to go through glTF community tools.
So seeing a lot of advantages and a lot of advances in current and future of all these graphic features. They're all very visual. And 5 years ago, glTF had no program to get the capabilities of the assets out and developing tools for the people in the community to use them. Otherwise, everybody would have to hand edit glTF files, which is really a non-starter. Wrong direction. So 4 years ago, out of 3D Formats, which is a group that oversees glTF, they formed the tooling subgroup. And that group is to promote the adoption and use of glTF for delivery and the use of 3D models. That was kind of a broad mandate to proceed, and so the group spent the first several months figuring out what exactly that meant and what to do. So we came across that it was very important to develop tools, exporters and importers, and other tools that directly process glTF, tutorials and other educational material, whether they be written tutorials or videos or anything else that worked for the community. And of course, we had to make sure that it was all easily available, so it's for the most part licensed either Apache 2 for the software and Creative Commons for the educational material. And then, and most importantly, we needed to promote that. And we took a couple of years to actually figure that out. We started with a number of tips that was somewhat successful, but much more recently we've had the wonderful efforts of Sandy Ressler as the 3D Formats outreach officer going through and promoting the tools primarily through LinkedIn. And not just tools, but all the work done in 3D Formats and 3D Commerce. In the education realm, we developed a number of videos or improved the existing tutorials. The first one is the 3D Commerce 3-part video series on getting people to use glTF models in their commerce applications websites. The 3 parts, delivering ROI, getting started, and tips for success, are all available on YouTube. What you're seeing here in a video clip is just the titles of the 3. Each video runs around 5-6 minutes and goes through what it does, what's necessary to achieve each of those goals. The video target audience is intended for business executives, people who have marketing control of what shows up on external references. Prior to that, we also developed a glTF tutorial series. This is on YouTube, and if you get the slides, this links to the YouTube playlist. There are 4 topics that we addressed. First off, what is glTF and how to use it? This is a real basic introductory video. Then there's 3 things for relating to the PBR work that was available at the time: clear coat, transmission, and volume. There's been a number of PBR advances since then, and so it's probably time to consider some more tutorials. If you have something in mind that you'd like to get educated, or you know of people that would like to get educated on that topic, that's really good to bring up to our attention. And you can do that through any one of the multiple reference mechanisms, either going to the GitHub repos for these, commenting on YouTube, or talking to me personally or any of the other people here. In the category of tools, we worked hard on a number of things. And one of our most important and visible tools is the glTF importer and exporter for Blender. This tool has been running now for about 8 years, almost, and has been fully supported through that time and is always brought up to date with the latest ratified extensions, at least that makes sense within Blender, the context of Blender. Right now, we're getting into looking exactly how we do things like interactivity and physics, and realize that we may not be able to do all those under the Blender hood because Blender is not supporting those, but except for those features, we're staying current. The sample viewer and separately, or not separately completely, but the compressor is one sample tool that shows how to do things. These are not reference applications. The compressor is built on top of the sample viewer, so when we expand and update the sample viewer rendering engines, it works without, it picks up the additional features. This compressor will take any GLTF file and allow you to interactively, in the browser, compress the geometry and or the textures. And this includes support for full KTX images, which is, in the context of GLTF, is basis U. An important part of the ecosystem is the GLTF validator. This will take your GLTF file and tell you if it's done correctly. It doesn't display anything, that would be the sample viewer, but it does go through and make sure that all the pieces are correctly aligned, that the pointers work to the right place, the lengths are correct, the byte alignment is correct. It's a very important part of the ecosystem for people who are building GLTF exporters or writers, so that you can ensure that you're doing it correctly. There's been a lot of support for KTX, and not just the GLTF version of basis U, but the entire KTX system. KTX is very good for holding images in the GPU and keeping them highly compressed. We are looking for other additional applications. We've identified some of them. If you have an application that is running short of texture memory in the GPU, we do have mechanisms for handling that, and there's a lot of different compression formats in this particular for those images. And finally, a lot of work has been done supporting PBR. In this case, much of the work is done within the PBR group, but there are occasions where some external work has to be done to prototype various models or texture and material capabilities. Lastly, in the area of content, we addressed several things. There was a blog post about a year and a half ago on tone mapping, which clarified how you should display models, not just GLTF, and has been adopted by a large variety of model viewers. And this was done by a person at Google who's now moved on to another job, but has been very standard and helped unify the display of models within the GLTF ecosystem. Comparable to that is the render fidelity application. This is another browser-based tool combined with some offline rendering. We run multiple different models and store the image results. The tool allows you to display the results of those renderings in a model against the model. In this particular case, it's illustrating a side-by-side swipe comparison. There are other more advanced comparisons in the works, including the ability to compare a single model in two different 3D viewers. So you can compare what it looks like in a path tracer and an online ray tracing application, rasterizer. Lastly, we have assets. We've developed 150-ish assets. 26 are showcase models, and the 6 listed here are considered showcase along with many of the previous assets. These are high or super high quality models with using advanced texturing, advanced PBR features. In some cases, some of the beginnings of interactivity is involved here too. So these are the assets that we use in our public comments, in our public displays on blogs, posts, and other things. This is a brand new website. It was released last week, just prior to SIGGRAPH. It allows you the easy selection, and it also supports the addition of, in this particular case, 250 or so test assets necessary to support physics and interactivity. It does this without displaying all 500, 600 assets all at once, but allows you to easily select them through the selection buttons at top or manual searches. Finally, looking at the whole part of this is to make the GLTF ecosystem more robust and support everybody's needs. We start off with the sample viewer and validator so you can visually see what your results are. It also verify that the results the GLTF file is being done correctly. You can check with the asset library, use the asset library for your own purposes. Almost everything in there is CC BY. You can also reference those, use them for your own purposes. in conjunction with the asset library, and this is something that Eoin has been working and used quite a bit, is he took some software that Microsoft developed several years ago called the Asset Generator and used it to generate assets that fit the test asset requirements. These test assets are primarily unit tests, so allow you to test your applications, test your designs, test your software, that you're doing it correct at a very low level without having to look at the final asset, in his case, the shaking lamp, and making sure that all the physics works from that step. Render fidelity application allows you to compare your renderer with other renderers, particularly those that are considered high quality, such as what you see in 3GS Model Viewer or Babylon, and also path trace renderers, so that you get a result that is comparable in quality or does reflect the particular needs and use cases of what you're trying to achieve. So I'll turn it over to Eric, and he'll discuss the 3D commerce use case development.
So I'm Eric Chadwick. I work at DGG. I'm a senior 3D technical artist there, and I've been in the Khronos group calls for about, since 2017 when I was at Wayfair. And so my job there is basically to help out with sample assets and making things that kind of stress test the system and make new images and see where we can push things and where they kind of fall apart and what we need to do next. So in 3D commerce, we basically work with e-commerce companies to figure out how can we use glTF and what's missing from glTF, what's missing from tutorial resources so people can learn how to use glTF effectively to market their products and create things, kind of experiences for customers. And towards that end, about 3 years ago, we built the first version of the asset creation guidelines, which is basically a set of guidelines for how to create 3D content that works in runtime, works in real time. You can use it in AR and VR, and things are performant but also look great. And what are the kind of the industry standard practices that are kind of accepted and should be shared across the whole industry? And so now we've seen, it's been a few years and things have changed, and we need to update those guidelines. So we're working on the next version of those. And then I'm going to talk about some of the e-commerce assets that we built over the last year. And then we revamped the website for the glTF sample assets, which Leonard showed briefly before. So the guidelines, basically we've got this list of things that basically help people create content. And it's basically aimed at artists who are basically making this content. How do they need to make things in order to actually make them work? And I love QR codes, so hopefully that's not too small and you can actually get a link out of it. But there's the link right below it as well. We would also love to hear from you, like what are the challenges you have in creating your 3D content for your customers? And what can we expound upon and find answers for to help you generate things? So this is it's in progress, right? But it's very visual heavy. We want to have visual examples that make it easy to understand what are the components that you need to do, how do you actually build this content, what are the things, more importantly, what are the things you should stay away from and not do. So we're going to have sections on alpha blending is a big problem in real-time rendering. When you have multiple layers, like these chandeliers up here, if I try to generate that in a glTF asset, you're not going to see all of those gems because you can't render all those layers on top of each other. So you have to take shortcuts to make it run in real time, and there are all kinds of caveats. And we want to hear back from you. So, things crash, things don't work great. We want to learn about what things don't work for you and what would be things that you'd want to learn about. And that's a QR code to go right to the issues page where you can actually talk to us and give us feedback. And then one thing I worked on the last year is creating 4 kind of what we called hero e-commerce assets. And we wanted to cover use cases that we haven't covered so far in the glTF sample assets repo. So we picked 4 items that we thought would cover a wide range of e-commerce use cases. So there's a kind of a commercial refrigerator there with glass that has kind of condensation on the inside and emissive lighting inside that you could turn on and off. A watch asset that has animated dial and has material variance and anisotropy for the watch band. And then iridescence with sunglasses, and then the car, which has a whole bunch of features, including variants in different colors. And we can look at a video if it plays. Let's see, how do you play a video? You just hit spacebar? Awesome. Okay, so this is the car asset. This started from a CC0 asset provided by UnityFan on Sketchfab, and I basically did a bunch of cleanup and then documented the whole process in the README in the glTF sample assets repo. So you can actually learn from it and figure out how to generate similar assets yourself. So I talked about, how does a shader work for iridescence, and what are the optimization processes in order to get all this stuff to work in real time and be something that works with variance. And how do you actually generate variance? Sometimes it's not that easy to make that. One of the other things I worked on here was the car shader. So the shader for the car paint, and it uses clear coat to get that kind of really shiny reflection on top of a rougher metallic specular response underneath it. And it uses a tiled normal map that has a bunch of noise in it in order to replicate the idea of metallic car flake paint, where you get those little shiny bits. We can't really do that in standard glTF, but we can fake it by using a normal map with a lot of noise in it, and then basically use point sampling for that. So I'm forcing that texture, we don't have the next one, but forcing that texture to be point sampled instead of, it won't play. Let's see if we do it this way. There we go. So the normal map is actually point sampled and everything else is MIP map sampled, so you get smooth blending. And it kind of works. It's not perfect, but it works most of the time, and it's helpful to get more complex PBR surface results. And one of the greatest things about this is we get to stress test what the PBR glTF model is able to do and is able not to do. What are the next things that we need to add to PBR to make it work for e-commerce cases? So we can look at the watch. And this was similar. How can we create something with variance that's interesting to look at and has a lot of material features in it? This uses the material variance extension again to get different color values from the same asset and make it very performant. So this file itself is, I think, under 12 megabytes or so, and it's pretty high res in terms of how much geometry is in there, and the specular response or the material response has a lot of visual interest, which is great. One of the things that really helps some of these assets is to limit how many textures you actually use in order to have a smaller asset that's much more performant, because when a customer is on a website, in an e-commerce website, and they're browsing products, they don't want to wait for downloads. So making it very performant and fast to load is really super important. And then occlusion mapping is really important in terms of a PBR material structure in order to have a believable rendering response. I think a lot of glTF assets, they just don't do occlusion mapping and don't think about it, but it actually is a very fundamental part of the PBR real-time material response and rasterizers. So it's kind of a really important thing to add, I think. And then the refrigerator, that was basically, I would love to do, something that has condensation on the glass. I thought that'd be fun to try. So this just uses roughness on the glass, and the transmission effect uses the roughness of the PBR surface to decide how blurry the transmission is. And so that's a really quick way to get something that looks like condensation. But then, because you're using the roughness, then you don't get that smooth glass surface on the outside. So I just added clear coat on top of the glass, and you get that secondary sharp specular response from the from the glass. And there's the roughness map. And it's basically just a rust texture that's applied to the glass. And really a lot of what works in PBR in order to create a realistic surface, a lot of the detail is actually in the roughness textures, because those decide how that specular response reacts. And then there's also emissive, so I baked an emissive map for this that's pre-baked, and that creates the lighting inside, and then when that's added to all the rest of it, you get a more kind of realistic lighting response. And I think that's it for that guy. So let's look at the next one. Oh yeah, so the sunglasses was a test of how really efficient can we get in terms of modeling. This uses hardly any textures at all. Only the logos are actually textures. Everything else is using really efficient modeling techniques. Oh yeah, and here we talked about the tone mapper before. So we developed the PBR neutral tone mapper, and it doesn't handle every use case perfectly. So for example, here we're getting some banding on the iridescence, whereas other tone mappers might not do that. But overall, the PBR neutral handles tone mapping a lot better for e-commerce use cases, because the color accuracy is very key for those people that are providing products, because what the customer sees, they want to get. And if they actually purchase a product and they have it in their hand and it doesn't match the visual thing that they saw on the website, often you'll get more returns that way. So the iridescence effect here is actually done, it adds to the glass and it makes it look opaque, but it is actually transmissive. So if you turn it off, you can kind of see more of the transmission going on behind it. And what else? This also uses something called face-weighted normal map, or face-weighted shading for the normals for the surface. So all those metallic surfaces have very limited geometry, and they don't use normal maps, which can add to the size of the file. So they actually use normals that are aligned with the largest faces of the surfaces. And so all of the light bending happens in the bevels of the surface. It has full transmission, so that's only on the glass. And what else? The base color. So the darker that the base color is, the less transmissive it is in PBR, in glTF PBR. So the darker that you make the base color, the less light is going to come through. And I think that's it for that guy. What else? Oh yeah, okay, so more QR codes to link. And here's a quick demo of I think this is the 3JS editor. They have a really nice material editing interface for glTF, so you can play around with things interactively. And that shows that the roughness on the glass transmission is what's making that condensation effect. And all of those are linked to the various READMEs for those. And so for each one of these, I documented how the process of generating these assets, what were the pitfalls I came across, what are the things that can be improved in terms of content creation workflows. And then the sample assets website. So we revamped that to make it easier to find sample assets. So it's all now searchable. You can use tags to search for specific extensions. So if you want to find everything that uses transmission, for example, you can easily find those assets to test them in your own applications. And each one has a live preview. So once you click on it, it becomes a live view that you can interface with the asset and look at the different layers that are in it, which textures and which different PBR features. And that's been a real group effort, which is a great part of these calls, is working together on solving these kind of things. And I think that's it for me. I'm way under time, but hopefully we have more time for a lot of questions than answers, because I know that's great.
So that's the wrap up of the content. We'll go into Q&A, but before we do that, just to mention, if you're interested, again, to get involved, either in the working group itself, you can join the Khronos group. Khronos is open to any organization that wants to join. But the 3D commerce working group that Eric was just talking about is special because it's not a working group that creates a specification. It's feeding into the other working groups that we have inside Khronos, mostly the 3D formats working group with GLTF. So we're trying to make that group a little bit more accessible to the companies that may want to feed into the process rather than getting elbow deep in specification work. So we do need to charge membership dues because we're a non-profit. That's the way we actually do all of this work. All of the membership dues that we get feed directly into developing all of the work you've just heard about. But 4K, for $4,000 US dollars, hopefully isn't a big barrier for folks who want to influence and understand what's happening in 3D commerce and how GLTF can help. So that's the content. We have time for Q&A. We have a couple mics, and I see someone going to the mic already. Please, go ahead.
Hi. Is this on? Yep. Okay, thank you. So maybe it's more of a speculation than a question, but since you're implementing things like interaction and physics and all that kind of stuff, I kind of got reminded of good old VRML. So I was kind of wondering if that's, in your head, is that kind of like a future case where GLTF also becomes embedded media, just like video or images on the web that is supported natively by browsers rather than using engines, or is that something you'd like, at least?
Yeah, no, that's a great question. And Leonard, we were talking about this. You want to come?
So independently of Khronos' work through the W3C, they're promoting, at least at the development stage right now, a tag called model. This is to embed 3D content into web pages and to actually bring it out. It's being, the idea was developed by Apple to handle their model viewer, where they could have models actually come out of the web page into their 3D environment as you're looking at it through the glasses.
All right, yeah.
Khronos does not oppose this effort. There are certain restrictions and other requirements, and so it's unlikely to be fully advanced as what GLTF or many of the other model systems are capable of, but it does bring 3D to a web page very easily. Also, right now, there's a model viewer which is built on top of 3JS, which is a Google extension essentially to HTML, which does a lot of the same features, but it's an extension that you have to build into your web page as opposed to being available native to the browsers.
Yeah, it was just a speculation, but I thought maybe it was on your radar.
We are all quite aware of Vermal X3D heritage, and it's a lot of the things there were put in perhaps even before their time.
Oh, for sure.
And Khronos is responding to a lot of what industry demands are. So it is our time for these features.
Yeah, it's good that you focus on the things that you know are supported across all or most platforms, so that's good. Yeah. Anyway, thank you.
You're welcome. Thank you.
Yeah, I mean, I lived through the Vermal X3D as well, and I think it is interesting. I mean, because images and audio is natively supported in the browser, and I think what the W3C is doing is good. For the very simple use case, it's good to simplify that, and we're working there to make sure that GLTF is supported in that, along with any other formats that people are interested in. But 3D is different to those linear media types, right? Because with video, give or take, you can stop and start, and then that's it, really, as long as you support the codec. Whereas the 3D assets are, it's so much richer, the use cases that you typically want to do. It's not something you can preordain. You need programmability typically, but they're complementary, I think. Yeah, please.
I see a lot of advancements. That's great. That's the question for the GLTF default material. I was wondering, Eric, already you talked about occlusion maps in that watch asset, but that was ambient occlusion, right? So I was wondering about parallax occlusion, if there was a plan to bring that into the default material to fake that depth information, that displacement, because parallax occlusion mapping is in the Babylon.js engine. We use that together with glTF, but we need to enable it specifically, and it basically just encodes the depth information into the alpha channel of the normal map and uses one value for strength, I think. Is there a plan to bring that in the default material?
If you know, come up to the mic. Do we have a handheld mic for the panel, by the way? Is there another handheld somewhere? It'll be easier.
Whatever. I don't think that we haven't really considered adding parallax occlusion. That's kind of more of a renderer thing, and there's so many different ways to do it, right? There's I can't remember all the types, but there's some great demos that go through, and the performance implications of the ones that actually work really well. So it's kind of it's up to the renderer to decide to do that. We have talked about, in the earlier slides, we talked about adding quad support, right? And then allowing subdivision. And then naturally that would fall towards displacement mapping in real time, right? And so you could do that. Maybe displacement mapping is kind of the better way to handle it. But then, you've got a more weighty kind of asset to deal with. And just for displacement mapping, you typically need a 16-bit texture instead of an 8-bit one, and then so maybe that's a KTX2 format that we can also leverage and use in HDR values and textures. But we haven't really talked about parallax occlusion, I don't think, in the PBR material model. But it's good to hear about it, right? That maybe that's something that would really help out. Because there's normal mapping, and there's geometry, and there's not much else otherwise.
It gives a lot of more detail to the, additionally to the normal map, and with relatively low effort on the format, I guess, because you just, as I said, include one more channel in the normal map. Yeah.
Right. Yeah, that's a good suggestion.
Thanks.
A couple questions. First, do you know what render was being used in the asset examples that you had? Is that?
Oh, let's see. That was the glTF sample viewer.
Okay. So
yeah, so the reference renderer.
Viewer. Okay, great. And then
sample renderer.
No, sample viewer, but it's an example renderer.
It's it's an example renderer. So it's not really great for production use because it's not built for that, but it's great for testing all your assets to make sure they actually perform within the spec, right?
I was specifically interested in what looked like refraction. Is it doing proper refraction through?
Oh yeah, so transmission is cool because it's actually, let me see if I can go back to those and we can just look at it.
Or is it like a single bounce kind of a thing? And
yeah, what it does is it actually, it's an old school technique which basically, for a transmissive surface, you hide the transmissive surface, the glass, and then you render everything else to an off-screen target texture.
Okay.
And then you map that back onto the glass from the camera's perspective, and then you distort it using the normal map there or the roughness map. And it kind of looks like it's transparent, but it's not really. It's pre-rendered of all the other things pasted on top of the glass.
Okay.
So it's basically one pass, but it depends on the renderer. Like I know Adobe in their internal renderer that they use in Stager, they have set it up so that it uses multiple layers of that. So you can do, I think, 2 layers of transmission. So it renders it once without all the transmissive objects, and then it renders it with the back layer of transmission, and then it renders the front, that kind of thing.
Right, and then the other question was open PBR. I saw in the future, any kind of gut feeling on time frame for would it be coming, or is this going to be compatible? Or?
That's a good question.
Still have Henrik here? No, he's gone. Yeah, I can try, but do you want to try? Or someone knows better than me? So the glTF PBR model and Open PBR, they're actually quite close. There's only a couple minor things that I wouldn't know exactly what they were, but I have good authority. They're pretty close. And the PBR group inside glTF is actually working over time to figure out ways of actually closing that gap. So you'll be able to go between glTF PBR and Open PBR pretty seamlessly. I remember Henrik saying it's not always lossless, but no, over time I think it'll get closer and closer. No, we're trying to converge, and we're not ignoring each other. We're actively working to make that happen.
Great, thanks.
Yep.
Also, on that respect, the Material X work has been integrated to some extent into PBR, into glTF PBR. There's a glTF PBR node in Material X, so that if you use that for your material, it goes seamlessly. And that, of course, would also work through Open PBR. And we're working on the back part there, but of course, glTF PBR is a smaller space than all of Material X, so you're getting this small little blob in the Material X space. So if you could go outside of that, and if OpenPBR supports that extension outside of that space that maps back, then it wouldn't be able to move back into the glTF space. But overall, as Neil said, things are mostly around the fringes of in the edges rather than substantial differences between what they can and can't render.
Perfect, thanks.
Hi, two questions. One regarding the assets. When are the glasses going to be available to buy it? I'm just kidding. It was really cool.
So the assets are free. But if you want to contribute money to Khronos, we won't turn that down. The assets are all on the GitHub websites, and for the most part, they're CC BY.
Yeah, and you're welcome to 3D print them if you want.
Yeah, exactly.
You can 3D print your own glasses, but the iridescence you'd have to generate yourself. So.
Thank you. The question is for the render fidelity. Is there a place, maybe I'm missing to check the links and the resources from Khronos, but could we find like a roadmap or what are the changes in that for that project?
No, we don't track the individual projects because we don't want to limit or be tardy in what the individual developers, the other companies are doing. So we do have a path trace renderer from Dassault, and Dassault has their own roadmap of what they're releasing. 3JS has their own roadmap through Model Viewer. Babylon keeps it. So rather than trying to collect all that information in one area and keep it current, which is a major effort, sort of like Neil's glTF slide, we leave the links to those projects, and then you go explore those links on Microsoft's or whomever's site to find out exactly what they're doing.
Yeah, okay. Thank you so much.
Hi there, good morning. Great presentation. Thank you very much. Just a quick question I wanted to ask. What type of percentage or increase or overall kind of adoptability of using glTF as the primary format have you guys seen in terms of the different online commerce sites, whether that's like fully virtual assets like TurboSquid or CG Trader or anything like that? Have you, over the past 4 or 5 years, do you feel like the adoption has gained significant kind of speed?
Yeah, I do know that those big sites, and I can't name specifics, but we work with them in DGG in terms of automating the conversion of high-res assets from like 3ds Max and Maya and V-Ray over to glTF in an automated way. So they have giant libraries of these assets, and they want to provide them in glTF, or they want to use those glTF files for machine learning to figure out how can we generate more assets with a large language model, right? So they are definitely using glTF, and you'll probably see it a lot more in those online stores as a downloadable set.
Right, so it definitely sounds like it's a big priority for them rather than a...
I think, one of the things that was great about glTF is that it's, like Neil said, it's really well spec'd. And so you know exactly how to make glTF and how to ingest it and how to export it and import it. It's really very clear. And that makes it a very attractive format for interop, even though it's not meant for that. It's meant for last mile transmission. It's meant for, compression and for being ready for a GPU to ingest natively. But because it's so well spec'd, you have things like Blender and all these DCCs that can import and export. So it becomes a very attractive format. So I think, I see it across all those websites as another download option.
Awesome. Thank you very much.
Yeah, I mean, joking aside, I do spend quite a few hours maintaining that slide. And I do, trying to do diligence, every logo on that slide is real, not pretend. And so it's unusual to find a site that doesn't support glTF. Of course, many of the sites support other formats too. But it is increasingly rare to actually say no glTF. It is pretty much everywhere.
I have a question about the glTF interactivity and if the glTF validator is doing any validation against that node editor kind of experience.
The glTF validator is not currently working on interactivity. The spec is not at what we would call release candidate, so it's not stable, completely stable and finalized. And we don't push that to the glTF validator until we get stability there, because we don't want to repeat or redo work on that. On the other hand, we do have a number of interactive tools. In particular, there's a glTF interactivity graph editor that allows you to test that portion of things and allows you to visually see what's going on.
Okay, great, thank you.
And Eva, do you want to add anything? No, you covered it. Oh, okay.
For some of the material assets that I generated in the content library, I use Visual Studio Code as the editor of glTF because it's an ASCII file. You can edit it in any text editor. But in VS Code, there's this great thing from Cesium called the glTF extension something. I can't remember the name exactly, but it's a plugin basically for VS Code that enables autocomplete on glTF text editing as you go. So it warns you right away if you put in something that doesn't work, like you've missed a comma or you've declared an extension in some part of the file, but you haven't actually loaded in an extension used. So those kinds of things. So it kind of auto-validates as it goes along, and I think over time they'll keep adding to that tool and adding more auto-validation things for new extensions like interactivity. Because it ends up in a glTF file eventually, so all that kind of has to be supported.
And do you want to take a guess when it will be done? Can't put you on the spot.
So making some assumptions in that the interactivity specification is nearly in release candidate, and we expect that to be happening by the end of summer. We think the validator could be fully supportive of checking for interactivity by the end of this year.
I'll hold you to that.
I get the calendar.
Okay, cool. Any other questions? Great questions, thank you. Any others? All right, so we'll call it that, and we'll give you 10 minutes back before lunch. So come on back if you're, we have a fun-packed afternoon, begins at 1 p.m. We have, let's see, Anari, OpenXR, Vulkan, Slang, machine learning, acceleration. There's a whole bunch of stuff, and it's goes on all afternoon. So hopefully you'll come on back. But thank you for being here this morning. Thank you.